everyone, in this video we're going to go over section 4.8, Newton's method. So we have solutions, or we have a means of coming up with exact solutions for polynomials of degree 4 or less. For example, if we had the polynomial ax squared plus bx plus c, and we wanted to find its roots, we know that the solution, or the solutions, are given by x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Similarly, we have nice closed formed solutions for some polynomials of degree 3 and of degree 4. But once we get to degree 5 or higher, we actually don't have a means of solving them by hand. We have to come up with the means of approximating the roots of degree 5 or higher polynomials. That's exactly what Newton's method is going to allow us to do. It's going to give us a means of approximating roots of polynomials of higher degrees. It'll allow us to solve things like 48x times 1 plus x to the 60th minus 1 plus x to the 60th plus 1 is equal to 0. So the theory behind Newton's method is this. A function and its derivative are very similar at a point. So let's say we wanted to figure out, and this is our function f of x that we're trying to find the root for. So what Newton's method is this. You guess a value of this root, and I'm going to call your guess x1. What you're going to do is you're going to find the point on that curve that relates with this value of x, and we're going to find the equation of the tangent line at that point. We're then going to use this tangent line, I'm going to call it L, and we're going to find its x-intercept, and we're going to call that x2. We're then going to find the point on the curve f of x that has an x value of x2, and then we're going to find the equation of the tangent line at that point. And we're going to recursively find equations of tangent lines and their x-intercept until we get closer and closer to this value of x. This all hinges on the fact, I'm going to draw the same picture again, that a derivative is always going to point towards a root. So this is our function f of x. Whenever we find the equation of a tangent line, it's going to point straight towards a root, or the x-intercept is, even if we're going in the other direction. If we find the equation of the tangent line here, and if we find its x-intercept, it's always going to be pointing towards a root. And as we get closer and closer and closer to the root, the x-intercept is going to approach the root of this polynomial. Now, the strength is, it's really easy to find roots of linear functions. We're just dealing with y is equal to mx plus b. If we want to find the root of a line, we want to find the value of x when y is equal to 0. Or we get that x is going to be equal to negative b divided by m. So it's really easy to find the x-coordinate of an x-intercept for a line, but it's very difficult to find roots of polynomials of higher degrees. But tangent lines and polynomials are very, very close, are very, very similar close to a point. So if we zoom in kind of with a microscope, if you will, there will be a point where this tangent line is so close to this polynomial, and this x-intercept is so close to this root that they are effectively the same. For what we're going to be doing, they are going to be close enough. This isn't about finding exact roots. This is approximating a root within some error, or to some degree of accuracy. How accurate you need is going to be ultimately dictated by what you're doing. We're just developing the method. We're going to go through the process, and we're going to use Newton's method to find roots to any level of precision. I believe in this In this lecture, we're going to find roots out to 8 decimal places. So here's the idea, but with greater detail. This is the graph of f of x. Its domain is just x is less than 7. I didn't want to have any of the graph floating around over here. So notice how when x is equal to 2, f of x is equal to 0. We know what the root for this equation is. We're just going to use Newton's method, or I'll show you the picture of Newton's method so you have an idea of what's going on. The first step in Newton's method is guessing a value of x, or guessing the root of an equation. You can use curve sketching. That's what I'm trying to say. You can use what we've learned up to this point to get a sketch of the curve, and then you can have an accurate guess about what the root is. You can also use online applications to plot your equations and get ideas of what roots are that way. But you make a guess about the root of the equation. So in this example, we're going to guess 4. So I guess that when x is equal to 4, this equation has a root. And so with x is equal to 4, what we want to do is we want to find the point on the curve f of x where x is equal to 4. And we get this point, the point 4, comma 1.333. When we find the equation of the tangent line through that point, we get this green line. And now what we do is, notice how this green line, the x-intercept, when we go to find the x-intercept, it brings us closer to the root of that polynomial. So when we go to find the x-intercept of this green line, we get this point, 2.80. Now what we're going to do is we're going to find the point on this red curve that has an x-coordinate of 2.8. That's up here. And now again we're going to find the equation of the tangent line that passes through this new purple point. And that's this line. Once again, I'm going to zoom in. We're going to find the x-intercept of this purple line. That's this point right here in black. 2.1280. We're going to find the point on the curve f of x that has this x-coordinate. That's up here. 2.128, 0.0525. And then we're going to find the equation of the tangent line again through this point. And now you can see by the third time we've done this, we have to zoom in pretty far for us to even tell the difference between the tangent line and the original curve. But we can repeat, zoom in more, we find the x-intercept of this tangent line, 2.00330. We map this point up to the curve, f of x, and it gives us that point, 2.0033, comma 0.001321. Then we find the equation of the tangent line through that point, and we get this orange line. And now Desmos actually doesn't have the ability to give me any finer precision. As far as Desmos is concerned, at this point f of x and this line are indistinguishable. And this we got to this level by the fourth iteration of Newton's method. So it's a powerful technique for finding roots. It all hinges on a good guess, though. If you guess poorly, Newton's method can fail. It doesn't always work. So like I said, it hinges on a good guess. You have to at least have an idea of where a root is for it to work. So the strength of Newton's method is that there's a simple algorithm to produce the results that we want. So the equation for a tangent line to a curve f of x at a point x1, f of x1 is given by y minus f of x1 is equal to f prime of x1 times x minus x1. And now Newton's method is we take the equation of the tangent line and then we find its x-intercept. Well, its x-intercept has a y-coordinate of 0. So that means we're trying to solve for x when y is equal to 0. Solving for x, this gives us, we'll divide by f prime of x1 that gives us x minus x1 is equal to negative f of x1 divided by f prime of x1, or we get x is equal to x1 minus f of x1 divided by f prime of x1. And since we use this as our next guess, we'll call this x x2. Now, we could repeat. Now when we want to find the equation of the tangent line through this point, we'll get the equation y minus f of x2 is equal to f prime of x2 times x minus x2. And if we set y equal to 0, we get this. And through the same algebra and the same way of defining x3, we would get x3 to be equal to x2 minus f of x2 divided by f prime of x2. So, in general, we get f of x sub n plus 1 to be equal to x sub n minus f of x sub n divided by f prime of x sub n. So now we have a nice formula that'll give us a means of, not f of x plus n, I'm sorry, our next guess. X of n plus 1, and I'll rewrite that again. X of n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. Perfect. So now we have a nice formula that will produce our next guess. This is convenient because this is very simple this is very simple to program a computer to do. You need a little for loop. You'll have to have some condition on when to stop, but this is a nice, simple thing to program a computer to do. So, if we have some function, f of x, and we call its root that we're after r, and the series of guesses we produce, they'd be like x1, x2, x3, and this would continue, x sub n. We say if the sequence of x sub n, so if the sequence of x sub n becomes close to r, as n becomes large, we write the limit as n goes off to infinity of x sub n is equal to r, and we say that the sequence converges. So, like in our previous example on Desmos, the values of x that we got, they started at 4, went off to 2.8, then 2.128, and then 2.0033. These values kept on getting closer and closer and closer to 2. So we would say that this sequence converges, and we would say that this sequence converges to 2. You might also see this notation, the sequence of x sub n, as n goes from 1 to infinity, goes to 2. Some texts, and I haven't seen it in our book, uses this notation for sequences. Newton's method, like I said, might not always work. So in this example, and I want to get this one, we'll do this. So if you make a poor guess about a root, Or if you happen to make a guess where the slope of your tangent line is close to 0, f prime of x sub n is approximately 0, you can, if you've got a relatively flat slope, you can shoot, or you might get shot way, way out of even possibly the domain of your function. So in a practical note, if you were to program this in a computer, you would just program a condition about the slope. If your slope is really close to 0, you might restart this algorithm with a new guess. And you would have to always consider the actual domain of your function. In this case, our domain is just from this point forward. And it's possible for Newton's method to return a value outside of the domain of the original function, because after all, we are really working with a bunch of lines, trying to use these lines to gain information about a function. For all of your homework, I believe you're given a start value, but these are just things to be aware about. I don't want to say the entire study of, but if you're onto engineering, if you're on into physics, applied mathematicians, this is all covered in a branch of mathematics called numerical analysis. In numerical analysis, they talk about different numerical methods for solving roots of equations, especially when you get into different differential equations, partial differential equations. Some equations you can't come up with nice solutions for, so you have to use these numerical methods to solve them. Let's start with an example. So, example 1. Starting with x1 is equal to 2, find the third approximation, or find x3, to the root of the equation x cubed minus 2x minus 5 is equal to 0. And our formula, our algorithm, is x sub n plus 1 is equal to x sub n minus f of x sub n divided by f prime of x sub n. So that means x2 is going to be given by x1 minus f of x1 divided by f prime of x1. And then x3 is going to be given by x2 minus f of x2 divided by f prime of x2. So this is going to be our roadmap to get where we want. So we have this f of x thing. So if we're trying to find roots of the equation, x cubed minus 2x minus 5 is equal to 0, that means our function is going to be f of x is equal to x cubed minus 2x minus 5. Okay, no equals 0. You trade the equals 0 in for an f of x. And what we're after is we're looking for values of x that make this thing equal to 0. Well, we have an f of x, but if you look, we need a derivative. We need an f prime of x. F prime of x is equal to 3x squared minus 2. So now we have everything we need. Let's put it in. Let's put it into the algorithm where it goes. We know x2 is going to be equal to x1, which is 2, minus f of x1. That would give us 2 cubed minus 2 times 2 minus 5, all divided by f prime of 2. 3 times 2 squared minus 2. Once the smoke clears, that is going to be equal to 2.1. Now when we want x3, x3 is going to be 2.1 minus 2.1 cubed minus 2 times 2.1 minus 5, all divided by 3 times 2.1 squared minus 2. You'd plug that into a calculator, and you would get 2.0946. So this is our third approximation to the root of this polynomial. We're going to recursively apply this algorithm over and over and over again. We'll do it 3 times, we'll do it 6 times, we might do it 8 times, but it all hinges on a guess, and once we make our guess, we're really just turning a crank. We turn the crank as many times as we're told to. So, example 2. We're going to use Newton's method to approximate the 6th root of 2 correctly to 8 decimal places. So to set up this problem so we can actually use Newton's method, if we want to approximate the sixth root of 2, let's give that thing a name. We'll call that thing x. And we're after the value of x. Well, let's raise each side to the power of 6. That says x to the 6th is equal to 2. And finally, let's make this thing equal to 0. We can subtract 2 from both sides to get x to the 6th minus 2 is equal to 0. Now, this looks like example 1. What we do is we call f of x to the 6th minus 2, and we'll need f prime of x. That would be 6x to the 5th. So now we need a guess. So the square root of 2 is about 1.4. So I think guessing x1 to be 1 is a fine guess. It's in the ballpark of where I think the root is going to be. So after I make a guess, complete guess, an educated guess, I want to say that, educated guess, but it is still just a guess, we would get x2 being equal to x1 minus f of x1 divided by f prime of x1. When you turn the crank, that will be about equal to 1.1, 6 sixes, and a 7. x3, oops, that was xn, x3 would be about equal to 1.12644,368. x4 would be about equal to 1.2249707. x5 is about equal to 1.2246205, and then x to the 6th is about equal to 1.2246205. And notice how we had this repeat. I didn't say it, but if we want to use Newton's method to approximate that value correctly to 8 decimal places, then from this recursive process, you want to list your answers with 8 decimal places. If you count them up, there's 8 decimal places here. There's 8 decimal places here, 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 and here. You stop when you have a repeat. Once you have a repeat, because after all, these numbers, they go on forever. We just only listed the first 8 of them. Once the first 8 no longer change, that means you're accurate to 8 decimal places and you can stop. So really the tricky part, I think, in this one is the setup. Figuring out how you're going to use Newton's method to approximate this value. Well, we're after the value of x, and x is equal to the 6th root of 2, so we raise both sides to 6, and then we subtract 2 to get some equation equal to 0. You need some equation equal to 0. Newton's method is used for finding roots, so some of these can be tricky on how you actually do their setup, how to turn it into a finding roots problem. For our final example, we're going to find, to correct 6 decimal places, the root of the equation cosine of x is equal to x. So what we want to do is we want to find the value of x that makes this true. We're going to be working with the function f of x is equal to the cosine of x minus an x. We had to move both of these terms to one side of the equation. We could also, it's just as accurate to say that f of x is equal to x minus a cosine of x. You can work this entire problem because after all, we could either move everything to this side of the equation or that side of the equation. It'll work just the same. So if we want to figure out the value of x that makes this equal to 0, and we want to figure out what value of x makes both sides of this equation equal, you can graph these to get a good idea for your initial guess. Let me pull up a different window. So right here, I've got the graph of cosine of x in red and the graph of just x in blue. And if you look, if you're trying to figure out where these two are equal, that happens about when x is equal to 1. So let's take that as our initial guess. Let's just say x is equal to 1 is where these two equations are equal. Perfect. So if we take x is equal to 1, well, first let's get f prime of x. F prime of x is going to be equal to a negative sine of x minus 1. So if we take x1 to be equal to 1, we'd get x2 being equal to x1 minus f of x1 divided by f prime of x1, which would be about equal to, we'll do, and we want to list these out. We'll list it out to 8 decimal places, and we'll make sure it's accurate to 6. 0.7503637. You turn the crank again, x3 would be about equal to 0.7391128.9. x4 would be about equal to 0.73908.513, and x5 would be about equal to 0.73908.513. So it says out to 6 decimal places, 1, 2, 3, 4, 5, 6. This is our 6th decimal place right here. If you look, so at x3, and then here's our 6 decimal places. You compare the first 6. 750363, 739112. Okay, these did not match, so you turn the crank again. After you turn the crank, you compare the first 6. They match, they match, they match, they're different. As soon as they're different, you know that one didn't work, and you turn the crank again. And you compare the first 6. Match, 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 match. Also in this problem, it happened that we're actually correct out to 8 decimal places, but we just needed to compare the first 6. I don't want to switch back over to Desmos. You guys can back up the video and look at it. If we chose a better guess for x1, if we took x1 to be 0.75, then we would get x2 being about equal to 0.7391114. x3 would be about equal to 0.73908.513, which is right up there. x4 about equal to 0.73908.513. Notice how you get your answer on the 3rd step. You do have to calculate the 4th step to make sure that you're correct, but by having a more accurate guess, we didn't have to do the process as many times. So how good your guess is ultimately dictates how good Newton's method is. And it's possible, it is very possible that you're trying to find this root right here, and if you make an initial guess, it can shoot you off and give you a different root, root 1, root 2. So be very careful with your first guess. Like I said, for your homework, and I want to write it before I forget to, 7, 11, 15, 17 through 21 odd, and I'll put it up on Blackboard. How good Newton's method is ultimately hinges on how good your guess is. I'd like to think that it's kind of cool that now we have a means of calculating what the 6th root of 2 is by hand. Before, there was no way of getting this by hand. And now we can get it by hand, accurate to as many decimal places as you want. So I think that's pretty cool. There's plenty of other methods for trying to come up with roots of polynomials. Like I said, look into numerical analysis if these numerical methods interest you. Go off and practice this homework, and I'll talk to you next time. Bye-bye.